So from last lecture, okay. So we've been talking about the Laplace transforms for impulse functions, right? So we've been talking about the Laplace transforms for impulse functions, right? So and these impulse functions can be transformed according to the Laplace transform into an exponential functions, and what you can find are those lines on the table, which is line 20 on the table. If you take a function delta t minus a, it's going to be transformed to e power minus a of s by the Laplace transform. Okay, so that's the method of Laplace transforms. Okay, so now with this Laplace transform at hand, okay, so we've also been talking about convolution integrals, right? So we've also been talking about the convolution integrals, right? So the convolution integrals is kind of the transformation that's going to transform a convolution integral into products, right? So it's going to transform a convolution integral into products. So by convolution integral, it means the integral. Okay, so it means the integral, right? So it's appeared, right? So it's okay. So it means the integral of this form, which is the integral from 0 to t of ft minus tau of g tau d tau. You do a Laplace transform. It's going to be transformed to the transformation for small f, and the Laplace transform small g multiplied together, capital F of s multiplied by capital G of s. Okay, so that's the Laplace transform for convolution integral. Okay, so very interesting type of question. Okay, so very interesting type of question that can happen is this kind of question. Okay, so you can see here that it's a question that's asking you to find the solution of an integral differential equation. So this equation is like, and there's an integral in the equation, but there's also an impulse function, right? So you have to both the integral and the impulse function. And you would like to solve this equation by via both the integral and the impulse function. Okay, so this is not kind of easy question. Okay, so let's see. The question says that I want to solve this equation y of t, right? So y of t, right? So I want to solve this equation where you are going to have y of t. Okay, so y of t, and then it says that minus the integral of y tau sine t minus tau tau. Okay, so the minus the integral 0 to t of y tau of sine t minus tau d tau is equal to, okay, so it is equal to the delta t minus pi cosine t. Okay, so it's equal to delta of t minus pi cosine t, right? So you want to solve this integral differential equation, right? So, and there's a delta function here. So the key point here is that as I told you many times, you have to recognize this integral as a convolution integral. So you can simply say this is the convolution integral between y and sine t, right? So that's the convolution integral is equal to the product of delta t minus pi multiplied by cosine t. So that means you can do a Laplace transform on both sides of this convolution integral, right? So you can do a Laplace transform on both sides of this convolution integral, right? So once you do the Laplace transform, if you get Laplace transform of y minus Laplace transform of convolution integral is the product. So Laplace of transform of y, Laplace transform of sine t. And here, you're going to have the Laplace transform of delta t minus pi of cosine t. So what's this transformation? Well, if you look at the table, right? So if you look at the table for the Laplace transforms, does it have this delta t minus a multiplied by f of a? Well, you only have the function delta t minus a under the transformation. So you have to, this is kind of the tricky thing for the problem, right? So you have to really work things out for delta t minus pi multiplied by cosine t, right? So this is something you have to really work it out, okay? So how do you do this? Well, you can see that. Any questions? If you have any questions, let me know. Okay. So you can see that delta of t minus pi of cosine t, we've been talking about it in class, but in general, we are going to have, okay, so we're going to have this is equal to the integral from 0 to infinity of delta t minus pi, right? So cosine t multiplied by e power s and t integrating up to dt, right? So this is the according to the definition of this integral, right? So definition Laplace transform. Now, if this is the case, you can see that we can approximate delta function, right? So you can see that this can be written as simply e to the power 0 to infinity, right? So you have to have the e power minus s, right? So I'm going to write this one. Okay, so I'm going to write this one t as pi multiplied plus. Okay, so let's say s multiplied by pi, right? So s multiplied by pi, and then multiplied. Okay, so and then multiplied by e power minus s of t minus pi, right? So you can write it in this way, and delta of t minus pi. And if you write cosine t dt, so that's kind of this one. You can see that this is cosine t minus pi, right? So plus pi, right? So dt minus pi, right? So I replace the t by t minus pi, right? So and this one is you're going to see. You're going to see that when you integrate, right? So when you integrate this object, right? So you integrate this object, it will be just equal to e power minus sa cosine a, right? So that's we have been talking about it in a few lectures ago, right? So when we've been talking about it a few lectures ago, when we talk about the integral transformations, right? So for the impulse transformation. So what we have been talking about is really here, right? So what I've been talking about is really here. If you multiply, okay, so if you multiply a delta function, right? So if you multiply a delta function t minus t0 f t dt, it's going to be f t0, right? So if you apply that, okay, so if you apply that, you can see that this is going to be just the cosinuses of pi multiplied by e power minus s and multiplied by pi. It's a good parabolic. Okay, so this is kind of very important. It's kind of telling you that the Laplace transform of this delta of t minus a multiplied by f of t is equal to e power minus as multiplied by f of a, right? So you in the previous table, you just have Laplace transform of delta t minus a is equal to e power minus as, but you usually forget you are kind of hidden by this line, right? So that's this is kind of very important, right? So this kind of you have to remember that this Laplace transform table that's showing you here has a line 20, which says that delta t minus a is transformed to e power minus as, right? So and therefore, if you multiply delta t minus a, then under the Laplace transforms, it's going to give you e power minus as multiplied by f of a. Okay, so this f of a is not ignorable. Okay, so this is kind of important. If you come back to this equation, it means that this is e power minus pi s multiplied by cosine pi, but cosine pi is minus 1. So that's kind of equal to minus e power minus pi s. Is a good family? Okay, so that in the end, you get the relation that Laplace transform of y minus Laplace transform y multiplied by Laplace transform of sine t is e power minus pi s multiplied by minus sign, because there is a minus sign in front of it, right? So with the minus sign. So therefore, you just need the Laplace transform of sine t. So if you check the table, it's in line 4. Sine t is transformed to 1 over s squared plus 1. Okay, so it's transformed to 1 over s squared plus 1. So Laplace transform of sine t is equal to 1 over s squared plus 1. If you have that, then it tells you that Laplace transform y 1 minus 1 over s squared plus 1 is equal to minus e power minus pi s, which tells you that Laplace transform of y is equal to s squared plus 1 divided by s squared minus the e power minus pi s. So if we write it down, it's minus e power minus pi s minus 1 over s squared e power minus pi s, right? So you have these transformations, right? So that's a relation here is telling you that Laplace transform of y is e power minus pi s minus 1 over s squared e power minus pi s. Is a good favorite, right? So you have this. Now, once you have this, you can transform back. So y is equal to the inverse Laplace transform of e power minus pi s minus the inverse Laplace transform of e power minus pi s 1 over s squared. Is that good to everybody? Okay, so what's the inverse Laplace transform of e power minus pi s? Well, you have to look at the table, right? So which line of the table, which row, which column of the table should we look at? We should look at the column 2, right? So column 2, e power minus pi s. So it's this one. So the inverse Laplace transform is delta t minus pi. So this inverse transform is delta t minus pi. And what about this one? Well, for this one, you can see it matches the transformation table, right? So which line should we use? Well, line 16 says that if you multiply e power minus pi to a capital F, then you're going to transform like this. So it's really the case. So you have to draw a table, right? So let's say capital F of S is kind of transformed back into F of T. So if you F of S should take S squared, and then as e power minus pi S multiplied by capital F of S is transformed under the Laplace transform, you have to use ut minus pi multiplied by ft minus pi. You have to use this function according to the shift table of the transformation. So what is going to be the inverse Laplace transform of 1 over s squared? If you look at the inverse Laplace transform of 1 over s squared, you should look at the second column, right? So you should look at the second column of this table. So 1 over s squared is n equal to 1 here, so it's transformed back into t, right? So into t, just the 1 power of t. So this one, the function is just the t. So therefore, if you get e power minus pi s 1 over s squared under the Laplace transform, the inverse Laplace transform is going to be the t minus pi, right? T minus pi multiplied by ut minus pi. U is the unit step function. So that's kind of the same. Okay, so it's a u of t minus pi multiplied by t minus pi. That's the inverse Laplace transform, right? So that's in the end, you get your solution. Okay, so you get your solution y, which is going to be, okay, so which is going to be related to delta function, both the delta function and the impulse function, u pi of t multiplied by t minus pi. So this is kind of an interesting question, right? So this is kind of an interesting question. It involves a very important line of this table, which has been missed, in the table, but it is required that you remember this, right? So the delta function applied to t minus a multiplied by f of t is equal to e power minus as multiplied by small f of a. Okay, so that's the what happens to the delta function under the Laplace transforms. Okay, so this is kind of the example that I would like to show you. Okay, so this is the example that I would like to show you, right? So that's the example I would like to show you. Now here I listed kind of quite several exercises. Okay, so for you to practice. Okay, so to practice this exercise, it's good, nice to practice these exercises and see how much you can do here, right? So that's this is you can find these problems on the archive, the old homework problems. Okay, so that's kind of the everything I want to say for the chapter on Laplace transforms. Okay, so that's everything I want to say for the chapter on Laplace transforms. Okay, so now for the rest of today's lecture, okay, so because we're going to have a review, right? So we're going to have an exam next week. For the rest of today's lecture, I would like to call upon a short review of the chapter on Laplace transforms. Okay, so let's call upon a short review, right? So let's say a short review of the chapter on Laplace transforms. Okay, so let's do a short review of this chapter on Laplace transforms. Okay, so I'd like to show you this review sheet. Okay, so we like to show you this review sheet. What happened here is that a Laplace transform happens from a function f of t. Under the Laplace transform is going to be another function, capital F of s, right? So the Laplace transform satisfies the property that small f of t under this transformation is capital F of s. It is very important. It is very important that you know how to calculate Laplace transform in the sense that LF is equal to the integral 0 to infinity e power s and t multiplied by f of t dt. That's capital F of s, right? So it's very important that you know how to calculate this integral, especially, for example, if they give you the small f is going to be, let's say, an unit function, right? An impulse, let's say a jump function, right? So the f of t maybe is equal to some a value a if t is greater than c, is 0 if t is less than c, right? Greater or equal than c. How do you do this transformation, etc., etc.? So you have to be able to calculate Laplace transforms in a correct way, as you can do for any such exercises. Okay, so what happened here is that the argument, it's very important to realize that the argument S for the Laplace transform at least has to be positive. And sometimes it is even larger, right? So for example, if f of t is e power of at, then S Laplace transform of f is equal to capital F of t, let's say capital F of s, where s has to be greater or equal than a at least. Is a good travel, right? So greater than a, maybe a is even greater than 0. So that's what happens to the Laplace transforms. Okay, so the Laplace, the arguments for the Laplace transforms. Okay, so it's kind of important. And we'll be also talking about some very important features of Laplace transform. For example, this transformation is a linear, right? So it's a linear operator. And it's linear operator, so that means you have the following relation, that if you take alpha of f, you take a beta of g, you do a Laplace transform of these two functions, then it's going to be alpha Laplace transform of f plus beta Laplace transform of g, right? So that's the Laplace transform of alpha of f plus beta of g. And this has been very important because if you can consider the inverse Laplace transformation, capital F plus beta capital of g, it's equal to alpha of f plus beta of g. So that's kind of, and this can be written as inverse Laplace transform of f plus beta of the inverse Laplace transform of g. So this is kind of telling you that the Laplace transforms and both the Laplace transform and the inverse Laplace transform are linear operations, right? So they're both linear operations under the sense. Okay, so they're both linear operations under the sense. Now, why do we need Laplace transforms? Well, we need Laplace transforms mainly because we would like to use it and solve our differential equations. Okay, so that's very important thing to realize is this relation that Laplace transform is going to transform a derivative of the nth derivative of the function to s to the power of n of Laplace transform of f, right? So Laplace transform of f plus minus, right? So minus s to the power of n minus 1 f of 0 minus s power n minus 2 f prime of 0 minus dot 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 minus f to the power of n minus 1 of 0, right? So that's kind of how the Laplace transform is going to transform the derivatives, right? So into polynomial powers, including all the remaining conditions which are in these initial conditions, right? So this is kind of very important, and you can find this 3 lines on the table, which whenever needed, right? So f prime is transformed to this, f double prime, and in general the nth prime transformed to this. Okay, so now this is very important because that means that if you have a differential equation, right? So if you have a differential equation, you just have to apply the Laplace transform on both sides of this equation, and after that, you can kind of turn the equation into a polynomial equation. And with the polynomial equation and with the help of the inverse Laplace transform, it can help you to solve differential equations. So this is the major idea how to solve differential equations using the Laplace transforms. Okay, so here's the table of Laplace transform, which it was an old table. Okay, so but now we have been using this new table for the Laplace transform, which is here, right? So that's a new table for the Laplace transform is here. Okay, so it's kind of nice to review this table by yourself. Okay, so make sure you understand it. Okay, so then we've been talking about the unit step functions, right? So a unit step function is a function, right? So a unit step function. So we've been talking about the unit step functions, right? So the unit step functions, right? So a unit step function is ut minus c. It is equal to 0 if t is less than c and 1 if t is greater or equal than c, right? So that's a unit step function is kind of the jumps to 1 at point c, and before that point, this function is just 0, right? So that's the unit step function ut minus c, right? So that's a unit step function. And very important thing that we are going to talk about. We're going to talk about a differential equation with discontinuous right-hand side. So important thing is you have to be able to represent the right-hand side by unit step function. So unit step function can help you to build any discontinuous function, as we have seen in many of our examples, right? So in many of our examples, in particular, if the function is just flipped, right? So if the function just flips, then you have to consider 1 minus ut minus c. So somehow you have to be kind of very flexible with all these things, right? So with all these things. Now, important thing is that the unit step function under the Laplace transform is going to give you e power minus cs divided by s, right? So you're going to give you this function, and which is found on the table, right? So you can see that unit step functions are transformed to e power minus cs divided by s. Okay, so this is the Laplace transform for the unit step function. Okay, so that's Laplace transform for the unit step function. Laplace transform of ut minus c is equal to e power minus cs divided by s, right? So that's the Laplace transform of the unit step functions. Okay, so once you have that, this is very important thing is about the so-called shift table of Laplace transform. So remember here is that the shift table starts from small f. Okay, so it starts from small f. Now under the Laplace transform, okay, so under the Laplace transform, it is going to be transformed into a capital F. Okay, so into a capital F. Now there are two types of shifts. One type of shift, we call it the ordinary shift, where the f is replaced by ft minus c multiplied by ut minus c, right? So this is ordinary shift, and they are going to be shifted to the right by an exponential shift with a minus c on both sides of this sign. Okay, so and there is also another type of shift where you do an ordinary shift on the image, right? So we talked about this a lot in class. You do an ordinary shift on the image, then it will result in an exponential shift on a preimage. The problem here is that this minus c is this minus c, but this minus c becomes a plus c. So if you do a forward shift, then the shift preserves the sign of this c. And if you do a backward shift, the shift is going to change the sign. So what happened here is that, the shift table of this Laplace transform is kind of important, right? So if small f is capital transform into capital F, then you can shift the ut minus a multiplied by ft minus a is going to be shifted to e power at minus at multiplied by f of as multiplied by f of s. But if you do a backward shift, you just shift the s to s minus a, then this is e power at multiplied by f of t. Is that good, right? So the shifts are can be opposite signs between the differences of forward and backward shifts, right? So forward and backward. And this has been shown, the shift table of the Laplace transforms can also be found on line 16, right? So it's on line 16 as well as line 11 of the table, right? So line 16 and line 11. These are two very important lines for Laplace transform, simply because that you need it. Okay, so you need it in order to transform back and forth between many different functions when you solve the differential equation using Laplace transform, right? So we have already seen a lot of such examples in our class lectures. Okay, so in our class lectures, so this is kind of a crucial. Okay, so and we've been also talking about this practically. Okay, so practically, the partial fraction decomposition is kind of crucial, right? So it's kind of crucial for us to do the Laplace transforms, right? So an inverse Laplace, it simply says that if you decompose the denominator into a family of functions that involves either the product of first order or completing the square. If you have the first order, then you're going to have a decomposition that's kind of constant on the numerator. And if you're completing the square, you're going to have constant multiplied by s plus another constant in the denominator. Okay, so here is a general result for partial fraction decomposition. That if you have a ratio p over q, right? So where the q is multiplied is a factor multiplication of first order factors multiplied by second order factors, then you can always have the decomposition that for each first order factor, if you exhaust from the first order power to the largest power, each one is accompanied with a constant a. And if you have a quadratic factor which cannot be factorized further, then you have the b and c, where they have the numerator is a polynomial that's one order less than the denominator. Okay, so you can determine the ABCs by method of undetermined coefficient. Simply means that you calculate that and you compare the both sides of this expression. So the partial fraction decomposition is also kind of crucial, right? So the partial fraction decomposition, right? So the partial fraction decomposition. Okay, so it's kind of also crucial for many applications towards the Laplace transforms. Okay, so and finally, in the last two lectures of recently, okay, so this week and the end of last week, we've been talking about the impulse functions, right? So an impulse function is a function that transforms, that starts from this unit, this jump function, and in the end, it gets a function that's a 0 if t is not equal to 0, and it is the integral of this function is equal to 1, right? So the impulse function is a function, right? So delta of t is a function that more or less like this. It's 0 everywhere except at point 0, right? So point 0, it's infinity. But important thing is that the integral of minus infinity to plus infinity of delta of t dt is supposed to be 1. Is that good, family, right? So the delta of t, right? So delta of t is equal to 0 if t is not equal to 0, infinity if t is equal to 0, right? So that's the delta of t dt, right? So now once you have this delta t dt, right? So once you have this delta t dt, we have been talking about this very important feature. So these are three very important features of the delta function that we have been talking about, right? So the first thing says that the delta function is like a probe, right? So if you use delta t minus t0, you multiply f of t integrate, it will help you to read the value of f at point t0. So that's delta function is like a probe, right? So the delta function is like a probe. If you do an integral of delta of t minus t0 multiplied by f of t dt, it will help you to read out the value f at point t0. So delta function is really like a probe, right? So this is the first important thing. Now the second important thing is that the Laplace transform of delta of t minus a, as we have seen before, is minus e power minus, right? So a of s, right? So that's the Laplace transform. But we've been just talking about the hidden line in the Laplace transform table. If you multiply by another f of t, you're going to have e power as multiplied by f of a, right? So that's kind of these two lines, both of them are very important for you to calculate some of this Laplace transform. As this example they just showed you in the previous example, right? So the delta function transforms t minus t0 into something like this. But if you multiply the t minus t0 with g of t, you're going to have g of t0 e power minus st0. Is that good for everybody? Okay, so that's the delta function under the Laplace transform. Finally, we've been talking about convolution integrals, right? So finally, we've been talking about convolution integrals, right? So finally, we've been talking about convolution integrals in our example, right? So it's, what happened here is that a convolution integral between two functions is the function f of t minus tau multiplied by g tau d tau. And if you do the convolution integral, right? So if you do the convolution integral, it's going to transform the convolution integral into products, right? So the crucial thing here is that whenever you see an integral, right? So whenever you see an integral for your differential equation, right? So that's an integral. Whenever you see an integral in the equation, you must recognize which two functions are convoluted. That's the only thing you want to do is to recognize which two functions are convoluted. And once you recognize which two functions are convoluted, you can simply try do a Laplace transform and transform these convoluting functions into the product of two functions, right? And this will be very important for you to solve any differential equations with convolution integrals. You just do a Laplace transform and you will result in a product of two functions. Okay, so that's kind of the application for convolution intervals. Okay, so I would like to suggest you look through the lecture notes posted on Canvas, work through the examples on notes, and practice additional examples on notes, which I just showed you on the lecture notes. Also, a good benefit, right? So I would say it is a benefit for this pandemic is that now you have all the class video as much as possible posted online. So even if this review, today's review session, I will post this video on Canvas, which can help you to review it forever, right? So this is kind of the good thing for this semester, right? So if there is no such pandemic, you will not have these class videos posted online, right? So which is good for you to have a perpetual review for the lecture.